So the change in internal energy is the sum of the heat and the work. So let's talk about heat. So heat is a transfer of energy, of thermal energy in particular, between two things. We'll call them the system and the surrounding, and that transfer is due to a difference in temperature. So temperature and heat are not the same thing. Temperature is a measure of the thermal energy that a sample has. It's related to the kinetic energy of the particles. So heat will flow from the hotter thing to the colder thing until both of the things are the same temperature. That's called thermal equilibrium. They're the same temperature. And then there's no additional net transfer of heat. And we know this, by life experience. If you take coffee, hot coffee, and you put ice cubes in it, does the coffee get warmer or colder? It gets colder. The hot coffee transfers some of its thermal energy to the ice cubes. The ice cubes begin to melt and warm up, and at the end, you have melted water and coffee all at the same temperature, right? That's what's happening. So when a system absorbs heat, its temperature goes up. There's a change in the temperature. And so that's called delta T, the change in the temperature. The increase in temperature is directly proportional to how much energy came in. So here we have Q is the amount of energy, and here's delta T, the change in temperature. And this is the proportionality constant. So that is called the heat capacity, and that would have units of joules per degree Celsius or joules per Kelvin, because Q is in joules and delta T is in degrees Celsius or Kelvin. So we can define heat capacity, capital C, the heat required to change the temperature of a system by 1 degree Celsius. The larger the heat capacity, the smaller the temperature change. But the heat capacity depends on the amount of matter, right? It takes more energy to heat a big stock pot full of water to boiling than it does to just like a small half cup of water would take much less energy to boil, right? So heat capacity depends on the amount of matter, which we usually measure as mass. And so we can say that heat capacity is an extensive property, meaning it depends on the size of the thing, right? Well, that makes it not so very useful. So specific heat capacity, that's a capital C with a little S subscript. This is an intrinsic capacity or an intensive property of the substance to absorb heat. So heat capacity depends on amount of stuff. It also depends on the type of the material. The specific heat capacity no longer depends on the amount. So specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. And this is related to the original definition of a calorie, which is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. So there the units are joules per gram degree Celsius. We can also express this as a molar heat capacity, where instead of looking at how much heat to change the temperature of a gram, we're looking at how much heat to change the temperature of a mole. And that would be joules per mole degree Celsius. So these are intensive properties. They are intrinsic to the substance. They do not depend on the size. So the specific heat capacity is the one that we use the most in chemistry. So here's our equation. Q equals mc delta T. This is C sub S, but we just say C. mc delta T. So Q equals mc delta T, And I've had students tell me that that looks like MCAT. Q equals MCAT. If that helps you remember it, great. Q equals MCAT. So Q is the heat in joules. M is the mass in grams. This is the specific heat capacity with units of joules per gram degree Celsius. And this is not something that you remember or memorize. It's something that you look up when you need it. And here's an example of a table giving us specific heat capacities. So if we were doing copper, it would be 0.385 joules per gram degree Celsius. And then delta T is the change in temperature. So delta T, the delta means final minus initial. So it's the final temperature minus the initial temperature. The temperature can go up, positive delta T, or it can go down, which is a negative delta T. Mm-hmm.
I know that diffusion and temperature have a direct relationship, and obviously we don't need the rate of diffusion to find the heat capacity.
Mm-hmm.
But could we use the heat capacity to find the rate of diffusion?
Well, the rate when we the type of diffusion that we've been talking about is of a gas, right? And so that's a good question.
I was thinking about stuff like that because I'm in physiology, so we're talking about like diffusion all the time.
Yeah. Well, you can also think about, the transfer of heat as a form of diffusion, as in how fast does the heat transfer. And that would have some things in common with the rate of diffusion of a gas, but there's a lot of complicating factors in there. Yeah. But no, that's a really great connection to make. Yeah. Well, let's look at this because I forgot to point this out. Look at the heat capacity, specific heat capacity of water. 4.18. Okay, here's ethanol, which is also a liquid and a compound, 2.42. But all of the rest of these are less than 1. So energy, water's heat capacity is more than 4 times larger than the other substances listed here. Water has a really high heat capacity. And what that means is that water can absorb a lot of heat energy with only a small change in its temperature. So it can absorb a lot of heat. And this has a big effect on our climate. So this is a picture of the Golden Gate Bridge in San Francisco. And I think we probably all know this. It's usually cooler in San Francisco than it is here in the summer especially, right? So, San Francisco might be 68 degrees Fahrenheit when Fresno's 100 degrees Fahrenheit. And it's not that San Francisco is much further north of Fresno. It's only a little bit north. Why is their temperature so different? It's because of the water. San Francisco is surrounded by water on 3 sides, the San Francisco Bay and the ocean, right? So heat comes from the sun, energy. So the energy comes from the sun and it hits the things on Earth and begins to heat them up. The water can absorb a lot of energy and only change temperature a little bit. Whereas things like the metal of the bridge or the concrete, they absorb the same amount of energy, they're going to get much, much warmer. So essentially the water acts as a heat sink and it just will suck in all of this energy. And then what is also kind of neat is that, so the sun goes down, the source of energy is gone, and now you've got this warm water, and it can give back a lot of energy without changing temperature much. And so you see the daily temperature variation in San Francisco is more like 10 degrees. Like maybe it's 68 during the day and 58 at night, because all of that water moderates the temperature. Whereas here it was 100 during the day and it might be 60 at night. 40-degree change. That's why we're always so confused. It's like, no matter how you dress, you're going to be wrong sometime, right? So we just wear whatever we want. Water is used as a coolant, like in the radiator of a gasoline-powered car, because it can absorb a lot of heat from the moving components and transfer it away. Keep the engine from overheating. Anybody have any questions? So here's a practice problem. Lots of words. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. What would be a far easier way to figure out if this was gold? Density. You got the mass, drop it in a graduated cylinder of water and measure the volume and just calculate the density. But sometimes we do things the hard way. Okay, lots and lots of words. Let's highlight the numbers. So we've got 4.7 grams. We've got 57.2 joules. We have 25 degrees Celsius and 57 degrees Celsius. And it's saying, find the specific heat capacity, and then the part about being gold or not. So let's take these numbers out and label them. We've got 4.7 grams, we've got 57.2 joules, we've got 25 degrees Celsius, and we've got 57 degrees Celsius. So the equation that we use with heat capacity is Q is equal to mc delta T. So what should we label the mass? M for mass. Mm-hmm. What should we label this amount of energy in joules? Q. So this much heat, and heat is Q. Again, why? I don't know. It just is. So we've got two temperatures here, right? So both of these are T, but one's an initial temperature and one's a final temperature. Which one's the initial temperature? 25, and 57 is the final. And the words are telling us that. From 25, that's where it starts, to 57, that's where it ends. And we're trying to find C sub S. So we have this equation, and we're going to have to do some rearranging here. So if we divide by M and divide by delta T, these guys cancel out, the M's cancel out. Have to do the same thing over here. So specific heat capacity is equal to the heat divided by the mass times the change in temperature. So we know what Q is, 57.2 joules. We know what the mass is, 4.7 grams. What's delta T? It's the final minus the initial. So the final minus the initial. So yeah, 57, that's not a 7. 57 minus 25, 32 degrees Celsius. Delta T can be positive or negative, and we need to be careful and have the sign correct. So this got warmer, it's got a positive delta T, so 32 degrees Celsius. So again, you're dividing by two numbers down here, so be careful on your calculator. 57.2 divided by, open parentheses, 4.7 times 32, close the parentheses. And how many sig figs should we have? 2. Our mass has 2, and the temperatures, even the temperature difference, only has 2. And so 0.3803. So the specific heat capacity is 0.38. What are the units? J over GC, right? Because none of these cancel out. So they're all just still there. Joules per gram times degrees Celsius. And that's why it has those weird units, is because that's what the units of the other things are. Okay, so we found the specific heat capacity. How do we decide if this is gold? We're going to compare it, right? We're going to look it up because nobody remembers this. And specific heat capacity of gold is 0.128. Is this gold? No. What's it more likely to be? Copper. Copper's 0.385, pretty close to 0.38. So this is not gold. No gold. Not gold. Any questions?
If you ever forget like the formula, I guess you can also just go off of the units.
Yeah, you can. Mm-hmm. Yeah. One of, I mentioned that dimensional analysis was, I think, the most valuable thing I learned in high school. I learned it in physics class. And like Alexis just said, if you look at the units here, joules per gram degrees Celsius, well, we're calculating the heat. So that's joules. And so we want to keep the joules. We're going to have to multiply by something that's grams. That would be the mass. And we're going to have to multiply by something with temperature, which would be the change in temperature. So definitely a huge clue. Yep.
That's not always the case.
So 0.38 joules per gram degrees Celsius, and the answer is no. We're not talking about gas laws here, so we do not have to use Kelvin. But sometimes the book will give you Kelvin, and so I want to show you something. Because this is just kind of trippy. So these are two thermometers. All right, there's the red part. And so this is on the wrong side. This is 0 Kelvin, also known, it looks like OK, right? And then this is 273 Kelvin. So 273 Kelvin is 0 degrees Celsius, right? And 0 Kelvin is negative 273 degrees Celsius. They are offset by 273 degrees. When you take the difference, it goes away and it's the same. So the change in temperature in Kelvin and in Celsius is the same. So if we think this all zeros and 273s, that doesn't really make a lot of sense. So let's look at the freezing point and boiling point of water, right? So this is boiling, that's freezing. And on the Kelvin scale, this is 373 Kelvin. So if we take water from freezing and boil it, delta T is going to be 100 degrees Celsius minus 0 degrees Celsius, which equals 100 degrees Celsius. If we do that in kelvins, it's 373 Kelvin minus 273 Kelvin, which is also 100. That somehow seems wrong, doesn't it? The thing is that the degree, the size of a degree and the size of a Kelvin, exactly the same size. The only difference is where you put 0. So Kelvin is based on absolute 0. Celsius is based on the freezing point of water. Here's another problem. A 55-gram aluminum block, initially at 27 degrees Celsius, absorbs 725 joules of heat. What is the final temperature of the aluminum? Well, let's pull out our numbers. We got that, and this, and this. And we're looking for final temperature. So I've got 55 grams. I've got 27.5 degrees Celsius, and I have 725 joules. And, this is heat capacity, so Q equals mc delta T. Well, what's this? 55 grams. Mass. It didn't say the word mass, but we know that gram is a unit of mass, right? 27.5 degrees Celsius. What's that? That's the initial temperature. And they even said it is initially at this temperature. And then what do we label the 725? Q, that's the heat, right? Well, we're trying to find T final. T final doesn't show up in this equation, does it? But delta T is T final minus T initial. We know what the initial temperature is, so if we solved for the change in temperature, then we could figure out what the final temperature is, right? So we're going to solve for delta T and then use that information in another equation to find the final temperature. What are we missing? We've got Q and M. Yeah, we don't know what C sub S is. So we have to look it up, right? If it was on an exam, I'd either give you a table or put it in the problem, but this is not an exam. So we look it up. Aluminum, 0.903. So 0.903 joules per gram degrees Celsius. So I want to solve this for delta T. So I'm going to divide by the things I want to move to the other side. Delta T is going to be Q over the mass times the specific heat capacity. So here Q is 725 joules. You should always write the units in here. Here they're not tricking us with the units, but you never know what could happen. 725 joules, and down here we have the mass, which is 55.0 grams, and the specific heat capacity, 0.903 joules per gram degrees Celsius. The joules cancel, the grams cancel. What we've got here is 1 over degrees Celsius, which is equal to degrees Celsius. So delta T is 725 divided by the quantity, 55 times 0.903. $14.598. 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So I want the final temperature. The final temperature is equal to the change in temperature plus the initial temperature. Right, I'm going to add Ti to both sides. So that's 14.598 plus 27.5. Ooh, got it in there, just barely. So 14.958 plus 27.5. It's 42.078. Adding, we're going by decimal places, 1 decimal place, and this one actually also had 1 decimal place. So 42.1 degrees Celsius is our final temperature.
So if the question says instead of absorb, it kind of let go, that means it's a minus. So
Mhm.
with the Q as minus.
Yep. Yeah, so if it says it gives off this much heat, then our Q would be negative. This Q would be negative. And when we do all this work, we'd find out that the change in temperature was negative. Because if you're losing heat, you're getting colder, right? Any questions? We did that one. 42.1. So if you have two objects at different temperatures and they are in contact with each other, heat flows from the hotter one to the colder one until they both reach the same final temperature. The amount of heat energy lost by the hotter one is equal to the amount of energy gained by the colder one. That's conservation of energy. So what we can do is we can define one substance as the system and define the other as the surroundings, and we can say Q for the system is equal to Q for the surroundings but opposite in sign. So just like the delta E that we were doing, where the system lost, the surroundings gained, right? So here the system is the hot material and it loses energy, then the surroundings gain that amount of energy. So we can use this to measure heat capacities. So here we have a beaker with some water, right? And we put a block of metal that's hot into the water. The temperature of the block of metal is 55 degrees Celsius. Maybe we had it in an oven or something. We know what its temperature is. The water has a temperature of 25 degrees Celsius. Okay? So we have a hot piece of metal in this room temperature water. Energy is going to flow. Thermal energy will flow from the hot metal to the colder water, right? So Q for the metal will be negative. It's losing energy. Q for the water is positive, but the same number, just different in sign. So exactly what temperature change we see is going to depend on the mass of the metal and the mass of the water, and also the specific heat capacities of the metal and the water. So we know that the amount of heat lost by the metal has to equal but be opposite in sign to the heat gained by the water. So that's where we get this Q metal equals negative Q water. Well, what is Q for the metal? It's MC delta T. The mass of the metal times the specific heat capacity of the metal times the change in temperature for the metal. And Q for the water, negative, is negative 1 times Q for the water, is negative 1 times the mass of the water times the specific heat capacity of the water times the change in temperature of the water. Okay? So what we can do is we can measure the mass of the water, we can measure its initial temperature and its final temperature. We know the specific heat capacity of water. So we can know all of these things. We can measure the final temperature of the metal because it's going to be the same as the water. And we know what its initial temperature is. And we can weigh the block of metal. And so then we can calculate the specific heat capacity for the metal. And this is much easier than taking a piece of metal and trying to measure how much energy is coming out of it and what its temperature change is. That's not simple. So here's an example with copper. A block of copper of unknown mass has an initial temperature 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? So always read the question all the way to the end, and then go back and identify the numbers. Because we do need the words, but the numbers are almost always much more important. So we've got that number, and this number, and this number, and this number, and then identify what are we trying to find? The mass of the copper block. So the idea here, this is another place where ugly pictures can be helpful. So there's my beaker, and it's got some water in it, and it's got a copper block in it, piece of copper. So we've got things pertaining to the water and things pertaining to the copper, right? So what we know is that Q for the copper is going to equal negative Q for the water. Or you could express it the other way. You could say Q for the water is equal to negative Q for the copper. It all means the same thing. For both of these, though, Q is equal to MC delta T. So let's take these things and identify them. So this temperature, that's an initial temperature of what? The copper, right? So T initial for the copper is 65.4 degrees Celsius. So I'm going to use color here, but you might want to write, that looks like titanium. Ti for the copper. Okay, so we've got that. Beaker containing 95.7 grams of water. So that's the mass of the water, right? So the mass of the water, we can call it mass H2O, is 95.7 grams. Then we have this temperature, 22.7 degrees Celsius. Is that the temperature of the copper or the water? The water, and it's the initial temperature, right? So this is T initial for the water, and that's 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2. What's the temperature of the water or the copper? It's for both of them, yeah. So that's the temperature of the copper and the water, right? So we could say T final H2O is equal to T final copper, and that is 24.2 degrees Celsius. So we're trying to find the mass of the copper block, which would be M for the copper. So the way I usually do this is we write out Q equals MC delta T is equal to Q equals MC delta T. So we have the copper on the left, so we have Q for the copper times the mass of the copper times the change in temperature for the copper is equal to Q for the water times, what am I doing? Let's start that again. Q equals MC delta T. So this is the mass of the copper, specific heat capacity of the copper, change in temperature of the copper. That's better. I don't know what I was thinking. And this is the mass of the water times the specific heat capacity of the water times the change in temperature for the water. So we have the mass of the water, and that's like the only thing we have right now. Can we calculate delta T? Yeah, we can, because we know the final temperature for both of them, and we know the initial temperature for both of them. It's getting crowded over there. So delta T for the water is the final temperature, which is 24.2, minus the initial temperature, which is 22.7. So that's 1.5 degrees Celsius. That's a positive number. Does that make sense? Yeah, because the water's getting warmer, right? And then we can calculate delta T for the copper. Its final temperature is the same, 24.2, but its initial temperature was 95, no, that's the mass of the water, 65.4. It's always good to write everything down. 24.2 minus 65.4. Negative 41.2 degrees Celsius. Does that make sense? Yeah, because the water got warmer and that hot piece of copper got colder. So we can't just say, oh, well, I don't like negative signs, I'm going to ignore that. It's important. One of the delta T's is positive, one's negative, because of this thing here. Mass is always positive, specific heat capacity is always positive. The only place we can have the negative is in delta T. So here what we want to do is we want to solve for the mass of the copper, right? So we're going to divide by the specific heat capacity of the copper and the temperature of the copper, and then over here, divide by the specific heat capacity of the copper and the delta T for the copper. So I'm just going to, do some magic here, because those canceled out. Well, that wasn't very magical, was it? Technology thwarts me. Okay. The mass of the copper is equal to the mass of the water times the specific heat capacity of the water times the change in temperature for the water divided by the specific heat capacity for the copper times the change in temperature for the copper. So we have the mass of the water, we have delta T for both things. We don't have the specific heat capacity. We have to go look them up. So back to the table again. So copper is 0.385 and water is 4.18. Okay, so now we can plug all these numbers in. So the mass of the water is 95.7 grams. Specific heat capacity for the water is 4.18 joules per gram degrees Celsius. And the change in temperature for the water is 1.5 degrees Celsius. And that's going to be divided by the specific heat capacity for the copper times the change in temperature for the copper, which is negative 41.2 degrees Celsius. So if we check our units, degrees Celsius cancel, that mess cancels this mess, and we're left with grams. 95.7 times 4.18 times 1.5 divided by the quantity 0.385 times negative 41.2. Oh, I forgot something. I forgot the minus sign. Curses. So I'm coming up with a negative mass, which, is ridiculous, right? So I wrote Q equals Q, and I forgot the negative sign. There's supposed to be a negative sign here. And negative sign here. So I take this number that I got, and I multiply by -1, and I get a positive number. 37.83 grams. If we look at all of these guys, they all had 3 sig figs, right? But what happens when we subtract these two? We get down to 2. So this is just going to be 38 grams. Easy peasy, right? There's so many pieces, right? There's just so many things there, right? That's a big old mess, is what that is. This is how I like to do it, just keep it all as one equation, because I don't like writing numbers down. But you could also do Q equals MC delta T for the water, because you have M and you have C and you have delta T for the water, so you can calculate what Q is, right? And then you can change its sign and use that for Q for the copper, and then just solve a Q equals MC delta T. And that's absolutely fine as well. Any questions?
So is that how they pretty much determine the specific heat capacity?
Yes. Yeah. This pretty much is how they determine specific heat capacity.
Do you have like a tip for us so that we don't forget the negative sign?
Well, I mean, I would definitely write this down, right? So it's like money. A money transfer is negative for one person and positive for the other, right? So an energy transfer has to be negative for one party and positive for the other. And what'll happen here is when you forget that negative sign, you'll end up with a negative heat capacity. That means, like, if you put this object on a stove and you turned on the burner, the more heat you put into it, the colder it gets. No, nothing does that, right? That's impossible, right? Can't have negative heat capacity. Can't have negative mass.
With the keys?
I guess if you use the MCAT trick and just think like if you get a poor score on the MCAT, then
Yeah.
you'll be positive. Yeah.
Yep, that's an interesting application. You really want to write everything down. Yeah. been so much easier just to weigh the stupid block. Okay, we're going to finish this section. So that was talking about heat. We're going to talk about work. This is a particular type of work called pressure volume work. So this is when you have the force is coming from the change in volume of a gas, and it's pushing against a pressure. And this is the sort of work that is done when the gasoline combusts in an internal combustion engine. That's why it's called internal combustion, because the combustion occurs inside, right? So this causes an expansion of the gas, which pushes against the piston and causes it to move. So when a gas expands, delta V is positive, but the system is doing work on its surroundings, so W must be negative. So the equation here is W is equal to negative P external times the change in volume. And then this is where we end up using a different version of R sometimes. There's a relationship between a joule and an atmosphere liter. So 1 atmosphere times liter is 101.3 joules. I don't expect you to remember that. Just try to remember that it exists. So here we have an initial state of our gas, and it's expanding, right? So the volume is getting bigger, and it's pushing against an external pressure. So it's the change in volume times the external pressure, and because of how we define work, we have to have a negative sign in there. So a cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work in joules is done? Well, again, we got a bunch of numbers here. So we have 1.58 atmospheres. We have 0.485 liters. We have 1.245 liters. And we have 1.5. No, I already did that one. I don't know what I'm doing. So this is a pressure, right? It even says pressure. So we'll call that P. And these are both volumes, but one's initial and one's final. And they actually call them that. Initial volume, final volume. So the initial volume is 0.485, final is 1.245. So the equation is work is equal to negative P delta V. Well, what do you think delta V equals? It's the final minus the initial, because that's what delta always means. So we're going to take our final pressure, final volume, oh my goodness, and subtract the initial volume. We're going to get 0.760 liters. It was expanding, so it's getting bigger, so the change is positive. This is our pressure. So W is equal to negative 1.58 atmospheres times 0.760 liters. Which is negative 1.2008, and the units there are atmospheres times liters. And this equation will be given. You don't have to memorize that one. Well, we found the work, but we found it in joules. So we're going to have to convert this. Why is that work negative? What does negative work mean? It's being done by the system for the surroundings, right? Double check that one. 101.3. So this conversion factor will also be given. So we do that math, and we should have 3 sig figs here, minus 121.64, negative 122 joules. Any questions? Okay, we're just going to finish this. When fuel is burned in a cylinder equipped with a piston, the volume expands from 0.255 liters to 1.45 liters against an external pressure of 1.02 atmospheres. In addition, 875 joules is emitted as heat. What is delta E for the burning of the fuel? So highlighting the numbers, highlighting what we're trying to find. So we've got 0.255 liters, 1.45 liters. So that's an initial volume and a final volume. So we could calculate delta V, 1.45 minus 0.255, it's the change. .195 liters. And we're given a pressure. The pressure is equal to 1.02 atmospheres. Then over here we have something about heat. So the 875 joules, that's Q, right? Is that positive or negative? Negative. Emitted. You emitted money. Like money is floating away from you as you're walking through the parking lot. That's negative, right? That's not good. This is negative. So delta E is equal to Q plus W. And W is equal to negative P delta V. So we've got our pressure, 1.02 atmospheres. We have our volume change, 1.195 liters. This is in joules, and this is going to come out in liter atmospheres. Right, so I'm just going to throw the conversion in here right now. 1 atmosphere liter, 101.3 joules. Negative 1.02 times 1.195 times 101.3. Negative 123.47 joules. Does the sign make sense? It did work. It was expanding against an external pressure. It did work on the surroundings, right? So it's negative. So delta E will be our Q, which is negative 875 joules, plus negative 123.47 joules. Negative 9. Keep double tapping my Apple Pencil and it doesn't work on this program. So negative 998 joules. Okay. Any questions?